All right, so morning everybody, and my name is Neela Shah, and I'm a senior consultant with Foundstone. And what I'm going to talk here today about are some of the security issues that are fairly prevalent in the development industry, but the development community is not so much aware of them. So we're not talking about things like SQL injection, buffer overflows, or cross-site scripting, right? Which are fairly, I guess the developer community has a fair amount of knowledge about the same. A few subtle issues that still exist, and the developers don't know a lot about it. Right, so I guess I already spoke about the goal. The kind of motivation was that I do a lot of security assessments like code reviews or black box penetration tests. And a lot of times when we are discussing the findings with the development team, the development team are kind of surprised that we didn't even know that there could be issues like this. So, I mean, there's no way we could have even prevented it. So the idea here is to educate the folks about those issues, which are prevalent, but not a whole lot of education about it. So here are the main categories, right? We'll look at things like inter-process communication, synchronization, or launching new processes, a few issues about cryptography, a few about ActiveX controls, third-party controls, and thick client applications. Right, so while we are discussing the issues, essentially the kind of approach or the layout we have is we'll discuss the issue, so we'll understand what the issue is, what the impact is, right? Like from a developer's point of view, okay, here's the issue, why should I care, right? What is the impact? From a bad guy's point of view, what does he need to exploit it? What all things does he need to do? Some of the recommendations as to how to fix it or the base platform mitigations that are in place. And then if you are a developer or an architect or a manager, right, how do you go about identifying the issue, right, at a feature level, at a code level? So it's a fairly, I guess, technical talk. Wherever, I guess, the issue is specific to Windows or Unix, I would kind of break that out. So here's the first one, right, with the inter-process communication primitives. And the first one's kind of a socket hijacking. So sockets essentially are your inter-process communication primitives, which are most prevalent because they are available on most operating systems. They allow you to do bidirectional data transfer, right? Now, a socket is essentially identified by an IP address and a port, right? An IP address and a port get you a socket. Now, one of the things about setting up a server is that you need to know the IP address, right? Now, that can be a little bit of pain because if I'm a developer writing up a server, then I obviously don't know the listening address offhand, right? I have to write code to figure out the IP address of the machine I'm executing on and then bind to it. So essentially, the C library has this wildcard, and it's called inaddress_any. And what it does is it will bind your listening socket to all the IP addresses that are present on your machine, right? So if it has multiple NICs, then all of the IP addresses will have the socket listening on them. Now, the crux of the issue is that on Windows, by default, you can have more than one socket listening on the same port, right? So I'm going to kind of jump to the next slide, right? So here's your typical setup, right? The server starts up. The server uses the inaddress_any flag when it sets up the socket because it provides a great abstraction to the developer. The developer doesn't need to write code to figure out what's my underlying IP. If he says inaddress_any, then that's it. The socket's going to be listening on all IP addresses. He specifies the port, and the server is listening. The client obviously needs to know the server's IP. And it uses that, connects to the server, and that's it, right? It's all set up, and they can start communicating. Now, here's what happens in socket hijacking. So you have the server come up. It starts on in address any and the specific port, and now it's listening for inbound communications or connections from the client. Right, now you have this malicious application, right, which also starts up on the same server, right? It uses the same port to listen on, but instead of using in address any, it's going to use the specific IP, right? So 172.23.20.110 in this example, right? Now you would think at this point the OS or the socket library should return an error, because essentially you have two applications or two sockets binding to the same port. But on Windows, this isn't the case, right? By default, both the applications are running, both the sockets are listening, and they are both listening on the same port, right? Now your client starts up. The client obviously uses the IP to connect to the server, right? Now when it initiates the connection goes to the server, and you essentially now have this conflict, right? The server socket library gets the connection, sees it's going to the port 2000, for example, right? And it has to decide whom to forward the connection, right? Because there's a conflict here. There are multiple sockets waiting on the same port. So there's a conflict, and the socket library needs to resolve this. So the way it will resolve it is it will resolve it in the favor of the socket, which is more specifically bound. So if my incoming connection is for 172.23.20.100, and I have two sockets on the same port, one specifically bound to this IP, which is 172.20.23 IP, and the other in address any, the socket library will resolve it in the favor of 172.23 socket, right? So essentially what will happen is this other application, which is malicious, will get the connection, right? So at this point, what you have is essentially what you have done is set up a spoof server, right? The spoof server is running on the same machine, right? But in no way have you injected the client or you have tampered the client. The client is still using the same socket's IP address port that it would connect to, but the malicious server now gets the connection, right? So at this point, you have set up a spoof server. Depending on the transport protections, you could do a man in the middle, you could do eavesdropping. But at the very least, there is at least a denial of service, right? If the malicious application gets the connection and just lives with it or just drops it, all your legitimate clients are never going to get serviced. So at the very least, it's a denial of service. And then depending on what you have, you could do a man in the middle. Right. Now, so I guess we spoke about the impact. Now, to exploit this, right, an attacker at least needs, I guess, execute privileges on the server, right? The attacker doesn't need to have elevated privileges, but he at least needs to be able to connect to the system and run code on it. Out-of-the-box configuration only affects Windows, and on, I guess, Windows XP Service Pack 2 and later is more of the Unix way in terms of that ports 0 to 1023 are privileged ports. So if you had to hijack those ports, then you already need to have admin privileges for them. So those are kind of some of the mitigations present. In terms of recommendation, when you bind, like when you write your listening server, you want as far as possible to bind to a specific IP address, but it's not always possible because you typically don't know which IP address to use if the underlying machine has multiple NICs. So a more feasible option is typically the socket option exclusive address use. And if you essentially use this, the socket library on Windows won't allow multiple sockets on the same port. And identifying the issues, at a code level, you want to try and search your code base for the APIs bind, set socket options to see if it could be an issue for you. At a feature level, essentially, if you have a client-server application communicating using sockets, then it could be an issue for you. So that's kind of the socket hijacking. The other part of this is a named pipe hijacking, and it's similar to sockets, Essentially, name pipes are another inter-process communication primitive, similar to sockets, right? Sockets are more widely used, but name pipes are fairly widely used as well. They also allow you to communicate between processes running on different machines, bidirectional communication. Typically, though, name pipes are used to communicate between processes running on the same machine, but I mean, you could have name pipes to communicate across machines. One thing name pipes that can do on Windows is I guess, a fairly important security attribute that sockets can't do is on name pipes, a server name pipe can impersonate the client name pipe without needing the credentials. So a server name pipe can say, hey, run in the context of the client, and the client doesn't have to pass the credentials. So it's completely seamless. So in most cases, name pipes are used when you have a scenario where you want to write a server, a background server, right? So it's a Windows service or a Unix daemon, and you don't want to run it as root, right? Because if you have your service running as root, and if there was an exploit or there was a vulnerability in that, then essentially that would compromise the whole box. So you want to write the service, not run it with root privileges, so in line with the least privilege principle. So you write it with a guest account or a limited rights account. But then you want to serve the client requests with the client privileges to make sure your application works, right? So typically what happens is you have the server configured as a limited rights user service, and if the client connects, the server will impersonate the client. And this impersonation doesn't need any credentials. This is completely seamless, right? So the client connects, the server impersonates the client, and then the server essentially processes the client's request in the client's context, right? So typically that's the scenario where name pipes are used. And the impersonation privilege is the main reason why a lot of time name pipes are used instead of sockets. So let's look at the issue here. So unlike sockets, name pipes are identified by a name, right? The name is just a string. So when you have your server startup, it essentially says, hey, create a name pipe of this name and listen to incoming connections. The client uses the same name, the machine slash name pipe name, and it gets the connection. Once the connection is set up, they can go ahead and communicate. Also, unlike sockets, name pipes are completely securable objects. So with named pipes, you can essentially say that only administrators should be able to connect to this name pipe, or only guest users should be able to connect to the name pipes. So name pipes, you can completely secure them, who can read from them, who can write to them, who can connect to them. So there are a couple of problems here. So let's see the first thing. And so this is similar to the socket hijacking thing. So essentially you have this malicious application startup. It essentially creates a name pipe with the same name, right? So it's now listening. Now you have the server application startup, and the legitimate server also essentially says, hey, create me a name pipe of this name test and listen on it. Now again, you would expect the OS to say, all right, there is already a name pipe with this name, so return an error. But that does not happen, right? The OS, what it does is, instead of returning an error, will just return a handle to the existing name pipe, right? So the real server thinks that maybe it created the name pipe, but instead it isn't the case. The other thing what happens is, if the server, when it creates a name pipe, says that create a name pipe with this name and make sure that you apply the security ACL so that only administrators can connect and read and write from it, right? If the server essentially does that, and if the name pipe was already created by the malicious application, the OS completely ignores the security attributes. So the OS just returns it the existing handle and completely ignores the security attributes, right? So now you have your client, right? The client starts up, again, it's going to use the same name. And when it uses the same name to connect to the name pipe, because the malicious application started the name pipe server before, it will get the connection, right? So it's similar to socket hijacking. Essentially, what you have done at this point is set up a spoof server, right? Your malicious application gets the connection. At the very least, it's a denial of service, and then depending on the transport protection mechanisms, you could maybe do eavesdropping, you could maybe do man in the middle, right? So similar to socket hijacking. However, one thing that you can do here is, remember I was talking about the impersonation thing. The malicious application now can impersonate the client without the client's knowledge. So in addition to the typical spoof server scenario here, the malicious application can run with the client's privileges. So if the client was running with elevated privileges like admin or root, your malicious application is now root, because that impersonation is completely seamless. The server doesn't have to request the client, hey, I want to impersonate you, send me your credentials, nothing like that. It's completely seamless. So as compared to the socket hijacking scenario, that's an additional impact here, that there could be a privilege escalation attack here. The other insecure configuration, I think I already touched on that. The OS will completely ignore the security descriptor. So in terms of what the attacker needs to exploit this, again, first and foremost, like socket hijacking, the attacker needs to be able to run code on the server, right? The malicious code needs to execute on the server. So he needs to have an avenue to do that. Also on Windows 2000 Service Pack 4 and later, Windows XP Service Pack 2 and later, and Windows Server 2003, there is a SE impersonate privilege that the server needs so that it can impersonate the client. And by default, that's only granted to the admin group. So it kind of gives some mitigation against the privilege escalation attack. In terms of the remediation, you want to make sure that when you create your name pipe, you only create it if it did not already exist. Because if it already exists, then you're not really creating it. You're just getting a handle to the existing one, right? And from a client point of view, if you have a client-server application using name pipes, and your application doesn't use the impersonation property of name pipes, then when you create the client-side connection to name pipe, you can essentially say that, hey, connect to this name pipe server, but don't allow the server to impersonate me. So you can do a little bit of damage control there. Like if you are using name pipes, don't need impersonation, then you can turn it off. Identifying issues, if you are using name pipes, then potentially this could be an issue. And as I was speaking earlier, right, typically where it is used is where you have a service running in a limited rights user context, and then impersonating a client to serve its request. At an API level, if you want to look in your code, you want to look for create name pipes, create file, and impersonate name pipe client APIs. Right. Mutexes and events, right? So these are your inter-process synchronization primitives. Mutex is essentially your primitive which allows you to protect modifications or access to a shared resource. Right. So an example, a good example would be if you have a banking application and which does transactions, you want to make sure that every transaction updates the database exclusively, right? Because you have multiple transactions going through, you don't want the balances to be corrupted. So you want only one transaction to update the database at the same time. So how do you do it? You kind of use a mutex or another inter-process synchronization primitive, right? Events are typically used to signal an event. So events, one of the most common architectures where events are used, where you have a worker process and a monitor process. And all the monitor process is supposed to do is start the worker process if it somehow exited, or shut down the shut down the worker process as and when needed, right? So typically they would use events. So again, as with the name pipes, these objects are also completely securable. So when you create your mutex or event, you can essentially say, hey, only administrators should be able to lock it, unlock it, signal it, reset it, right? Similar issues here also, like if you try to create a mutex or an event, which are again identified by a name, which is just a string, if you did not use if it already existed, the OS is not going to return an error, right? It will return you the handle to the existing one. And the other thing, again, as in named pipes, it will completely ignore your security attributes that you specified. So the impact, again, depends on what you're doing with the object. So like in the banking example, if a malicious piece of code locked the mutex and did not release it, essentially it's a denial of service, right? Because your legitimate banking application will never get hold of the mutex and then never be able to update the database. Privilege escalation, this depends, but from where we have seen this happen is essentially the monitor worker process, where if a malicious process can signal a particular event, the monitor will listen and shut down the worker. So things of that nature. Again, to exploit this, an attacker needs to be able to run code on the server so that he can change the state of the object. And then recommendations, when you create a mutex or the object, then you want to make sure that it did not exist, and then apply your security primitives attributes to it. We kind of talked the typical applications where you can see these issues. And then at a feature level, you want to look at create mutex or create event, wait for single object, those APIs. All right, so going to the next kind of category, essentially involved security issues with creating new processes. So most commonly, right, where products or applications expose this functionality such as scheduled tasks, most times they will have this additional functionality that you can choose a process to run if the task succeeded or if the task failed, right? So the user goes into the product, selects the task, selects the time when he or she wants to execute it, and then selects an executable that it wants to execute if the job succeeded or failed, right? So a few issues here, right? So first of all, in most cases, what can happen is the scheduled tasks run at a different time, right, at your scheduled time. So at that time, they typically end up running with the local system privileges, which is how the Windows service is configured, or root if your daemon is a setuid daemon, setuid root daemon. So if that's the case, then essentially what is going to happen is your post-task execution will also run as root or local system, which is the most powerful account on Windows, and will result in a direct privilege escalation. The other thing what we have seen applications do is because they have the task execute or the process executing with higher privileges, they have a certain whitelist of processes that the user can choose. Now, depending on how you execute it, it still could be vulnerable. Like for example, on Windows, if you essentially have C:" program files, software, myprogram.exe, right? If you don't essentially launch it securely, what Windows will do is it will first look for the white space in your executable path name, right? So C:" program, and then there's a space and then files, right? So if it found a C:" program.exe, it will launch it and pass the remaining files, software, myprogram.exe as an argument to C:" program.exe. So you will essentially launch a different process, C:" program.exe, which might be malicious, instead of C:" program files, software, myprogram.exe. So that's kind of typically used to get around the whitelist validation. So the impact there really is privilege escalation, and I mean exploitation mitigations. You kind of need local access so that you can copy the malicious file. Or, I mean, you can, if you know like a powerful program, you can just run that. instead of copying it. So the recommendation there is to kind of launch the new process with appropriate privileges. So instead of launching the new process as root or local system, use the right user to launch it. And then launch it securely so that you don't launch c::program.exe instead of the c::program files application. Identifying the issue at a feature level, if you, as I said, right, the most common example is where you have your application has a scheduled task feature, which allows you to run post-execution files. That's at a feature level, that's one example. At an API level, it's kind of create process as user APIs. If you want to look at in your code, then those are your APIs. All right, so moving on to cryptography. So the first one in cryptography is your insecure cipher mode. Now, cipher mode isn't exactly your the cipher. Cipher mode is one step above the actual cipher, and it essentially determines how your cipher works, right? So, for example, in block cipher, what it essentially does is breaks down your input into blocks and then encrypts each block at a time, right? So we'll look at an example. So essentially, electronic code book is this very kind of primitive cipher mode, which is insecure. And the reason why it is insecure is because it can reveal patterns in your plain text. So I think I have an example. So essentially, here's your client application and a server application. It's a payroll application, and here's your user. What it does is it asks the server, hey, get the salary details. The server sends the salary details, but then again, the server wants to prevent this from eavesdropping or sniffing attacks. So it essentially sends you the ciphertext. The client application has the necessary decryption key to decrypt it and kind of show the plain text corresponding to that, right? Now, here's the attack scenario. It's the same client-server application. Here's your user, connects to it, asks for his salary details. Now, this malicious user is just sniffing on the wire, right? He sees the encrypted text, right? So since the application doesn't send out clear text, right? But if you look at those both cipher texts, now it's same, right? If the attacker had known the ciphertext in the first case, then he knows what it essentially means to in plain text. So the idea here is that in electronic code book, the same plain text results in the same ciphertext, right? So if I knew the plain text, then looking at the ciphertext, I know what the plain text is, right? So it's the same plain text with the same key will always result in the same ciphertext. So as an attacker, if I know that, hey, the plain text of $100,000 results in this ciphertext, if I see that packet or that string anywhere on the wire, I know this is an encrypted version of $100,000. So it kind of gives away information about the plain text. And so here's another kind of pictorial representation of the same, and this is from Wikipedia. So it's kind of your image, and then if you encrypt it using electronic code book, it kind of still reveals some patterns in the plain text. Right. So again, I mean, to exploit this, you don't really need local access. But I mean, in terms of recommendation, you want to make sure you use a strong cipher mode, such as cipher block chaining. A lot of times, developers use strong algorithms, but then a weak cipher mode kind of weakens the advantages of using a strong cipher. And identifying the issue at a feature level, if you are using cryptography, symmetric block ciphers, then potentially this could be an issue for you. The APIs kind of differ. If you're using the OpenSSL library, you have a different set of APIs. If you're using the Windows SDK, you have a different set of APIs. The next one is integrity checking. So this is most commonly seen in like today's thick clients, right? Almost every thick client today has essentially this auto update feature, where when you launch the client, it will go check if there is an update available. And if you say, go ahead and install it, it will go ahead, download the update and install it, right? So a few issues here, right? So if there's no integrity checking, right? If the update is just being downloaded of clear text, then potentially there's a man in the middle avenue there, right? Somebody could replace the update with a malicious file. It comes to the client is going to install it. The machine is going to be compromised, right? The other kind of subtle issue is their application does use hash or signatures to verify the integrity of the downloaded update, but it doesn't do it securely. So by that, what I mean is essentially the client connects to the server and says, hey, is there an update? The server says yes, and the server sends the update, right? So the update goes in clear text, and then with that, the server also sends the hash, right? The hash now, again, if it's in clear text, then an attacker has to go one step further, replace the update, and then replace the hash as well. Now when the client gets the update and the hash, if it verifies it, it will match, and it would still be compromised. So I guess, you want to make sure you use hash or signatures to prevent tampering of the update, but you want to do it securely. So when you transmit your hash or your signature, make sure you do it securely, right? The most common scenario is where an application will download the update over clear text, but the hash is only available over the SSL kind of connection, so that it can't be tampered. And impact is, again, mostly a compromise, because you're essentially installing a rogue update on the client machine. Right, and I guess we already talked a little bit about the recommendations. But as the client application, you want to make sure that before you apply the update, you ensure that you have obtained it from the right source and it hasn't been tampered before you update it. And most common scenarios where this could be an issue is your auto update, check for update scenario. ActiveX controls. Now, ActiveX controls are kind of, they are being used less and less, but there are still quite a few ActiveX controls out there. Essentially, I guess they allow you to execute code in the browser, but which is not running within the browser sandbox, right? So you can essentially run a Win32 application from a browser, right? So that's the great benefit or the power that ActiveX control gives out. Typically, though, ActiveX controls are used to kind of provide a rich interface. So like there are quite a few applications which want to show a tree view or Windows Explorer view, right? And for that, they will write an ActiveX control. So a common example is your document sharing application or a knowledge tracking software, where you essentially have drag and drop. So you drag from your local file system onto this ActiveX control. It will sync up with the server, right? So common example. However, the problem with ActiveX controls is one, again, it's a Win32 component, so it doesn't execute in the browser sandbox. So there's a great deal of motivation for exploiting ActiveX controls. The one issue is repurposing. So let's say I have a document sharing application. I write up an ActiveX control, which allows you to upload, download files, sync files between the client and the server. Now, my ActiveX control is supposed to be only executed from my website, which is, let's say, my documentsharing.com. Now, the very nature of ActiveX controls there's nothing stopping a evil site, so myevilsite.com, from using that ActiveX control. Essentially, you have this HTML tag or JavaScript tag which will run the ActiveX control if it's installed, right? So if an attacker tricked the victim to go to a malicious site, right, and the victim, let's say, has this ActiveX control, the malicious site is going to execute it without the user's knowledge, right, because it's already installed. So one of the things that you can do to limit damage with ActiveX controls is tie it to your site, right? So let's say you write an ActiveX control which is only supposed to be executed by your site. When you develop your ActiveX control, you can essentially say that this site should only be launched from mywebsite.com. Or you can essentially say this site should only be launched by any website in my trusted zones or any site in my intranet. So you can tie an ActiveX down. So that essentially limits the damage, right? Because if I have a very powerful ActiveX controls like document sharing, file uploading, file downloading, if as an attacker I can get a victim to my site, then I can use that ActiveX control to copy malicious files and compromise the victim's workstation or copy files off the victim's workstation. So that's one of the issues there. Initialization from untrusted sources are similar. Scripting, so you can turn off ActiveX control scripting, but if your ActiveX control is supposed to be accessed from a browser, in most cases you can't do it. This is typically a scenario where you write your ActiveX controls and then essentially through Visual Studio or another designer, you drag and drop on a form or on your window. Then you could turn scripting off. The impact really depends on what the ActiveX control could do. So you could have a bunch of different impacts there. Recommendations, you want to sign your ActiveX control so that when the user launches it or downloads it, he or she has the confidence that, hey, I am getting this ActiveX control from where I'm supposed to. Site lock template is essentially this template which allows you to tie ActiveX control to a site. And if you don't need, then don't mark it safe for initialization. At an application level, again, if you are using ActiveX control, then you're potentially vulnerable. All right, so third-party components. So third-party components, again, are a great way of rapid application development, right? Let's say I'm writing a product, and I need the compression feature or functionality to save on bandwidth, right? Now, I could write up my own compression routines, or I could write my own implementation of the already existing routines, or I could just get zlib. Zlib has been around for a lot of time. It's been used very widely. I can just integrate it in my app, and I have the compression functionality. So your commercial off-the-shelf components are fairly popular in that scenario. Now, the problem with this is, though, typically the way this process works is, let's say I'm in version 1 of my product, and I need the compression functionality. I'm going to take the latest and the best zlib version available today and going to integrate it. Now I am 5 versions down the line. I never had the need of any more compression functionality. So my version 5 is still shipping with zlib 1. Now zlib or any other third-party component is like any other software, right? There are vulnerabilities published, the vendor patches them, right? However, if essentially because this third-party component vulnerability is not followed, your application keeps on being vulnerable, right? So you want to make sure that someone on your team kind of subscribes to the advisories of these third-party components that you are using. And if there is a vulnerability published, then you essentially research it. If it's applicable, then patch your product so that your product is not vulnerable. So this is not a direct kind of this issue is not introduced in your application because of your coding or your design, per se, but because this third-party library that you are using is vulnerable. Right. OpenSSL and zlib are like the most common libraries that I've seen in most applications keep on using them, and many times they are kind of outdated. And finally, the thick client applications, right? Now, thick client applications are like typically if you have a server client which talks TCP, which does not talk HTTP, then you have to write your own client, right? If it talks HTTP, then you could use the browser, but otherwise you have to write up your thick client. Another scenario where thick clients are developed is because you want to develop a richer UI. The web is just not enough, the browser is not enough, so you write up your own client. Now, the problem with thick client is thick client really can become a thick client. So you can have things like authorization checks all pushed to the client, right? So which menus to show depending on the role of the user, they all get pushed to the client sometimes, right? And client, by the very nature of it, should not be trusted, right? Because client, you don't control the environment in which the client runs. An attacker might be able to reverse engineer it, modify it, comment all your rule checks, and you don't want that to happen. Another scenario with thick client, though, is a lot of thick clients, even today, seem to need admin privileges to run. Now, that's a problem because typically you don't want, network administrators don't want to give out admin privileges to everybody, right? If I need admin privilege to run a client application, then that's probably going to need, in most environments, network administrator sign off saying that, hey, this guy has been given admin privileges. And a lot of times it's also because the log file is stored in program files directory, or a registry key is in HK, like HKey local machine, or I'm creating a listening socket on ports, privileged ports 0 to 1023, all which could be kind of tweaked around, right? So again, the impact, if you have authorization, data validation checks in your client, then that could be more serious. You could result in privilege escalation. And the other impact with having admin privileges necessary for thick clients is that if there was a vulnerability, then your machine is going to be compromised because it's running as an admin. And then in terms of remediations, you want to make sure that, I guess, both of those issues are kind of resolved. So storing your logs in user's document directory, if you set up a listening server as part of your client, then use one of the higher ports instead of privileged ports. And then I guess if you are using a thick client, then potentially these could be a concern. These are some additional references. That's pretty much all I had. Any questions, comments? No? All right, that's pretty much it then. All right, thanks for being here.